All right, let's dive right into this step-by-step explainer. We've designed this to be your ultimate roadmap for conquering Lab 4 in your embedded system design course. Today, it's all about input/output port programming. You know, if you've ever wondered how the software you type into a computer actually reaches out and touches the physical world, how it physically turns on a motor, reads a sensor, or flashes an LED, well, this is exactly where that magic happens. We're going to unpack your lab materials and turn them into a totally actionable guide.
We're essentially treating this lab like leveling up in a game. We'll start simple with basic I/O, move into manipulating that data, step it up by generating square waves, and then tackle the big one, PWM signals, before wrapping everything up. Let's get started.
So, kicking things off with Level 1, Basic I/O.
Take a really close look at this assembly code. Notice how it starts by moving the hex value 0FF into the accumulator, and then moving that directly into port 0. Why do we do that? Well, because in this specific architecture, writing all ones is actually how you configure port 0 as an input port. It's a fundamental hardware quirk you absolutely have to remember. Once it's configured, the program enters that loop labeled back. It grabs the data coming in from port 0, moves it to the accumulator, and instantly pushes it out to port 1 before jumping right back to the start. It's basically an infinite mirror, reflecting your input straight to your output.
To clear this first level, your immediate task is to actively rewrite this example code into your development environment. And hey, don't just copy and paste, actually type it out so you build up that muscle memory. Then debug it and simulate it in your Keil software. Your goal during simulation is to physically observe output port P1 reacting in real time as you manually flip the inputs on port P0. Seeing those simulated pins toggle based entirely on the code you wrote, that's your first major victory for today. Moving right along to Level 2, Data Manipulation.
Now, here is where things get really interesting. You aren't just moving data from point A to point B anymore, you're changing it on the fly. You need to take your continuous read from port P1 and perform an exclusive OR, an XOR operation, with the hex value 0FF before pushing it to port P2. As an engineering student, you probably recognize right away what XORing with all ones actually does. It perfectly inverts every single bit, so if a switch is flipped on, the corresponding LED goes off, and vice versa. This is a super practical lesson in intercepting and altering hardware signals using basic bitwise logic.
Okay. Time to level up again. Level 3, Square Waves. For this level, precision is absolutely key. Your code needs to be laser-focused on one specific physical pin, output port P2.2. You can't just blast data to an entire 8-bit port anymore. You have to address a single bit, making sure you leave all the other pins on port 2 completely unaffected. Depending on how you approach this, you'll need to use careful bit masking or specific bit-addressable assembly instructions. Your specific engineering constraint for this level. You have to write a program that pushes out a square wave running at exactly a 1 kHz frequency on that specific pin. Think about the math for a second. A 1 kHz wave means one full cycle takes precisely 1 millisecond. And since it's a square wave, it has to be perfectly symmetrical, high for half a millisecond and low for half a millisecond. You're going to need to calculate the exact machine cycles of your microcontroller to write a perfectly tuned delay loop. Or, honestly, even better, configure a hardware timer to do all that counting for you.
So, you've handled static data inversion, you've generated a perfectly symmetrical square wave, but are you ready to tackle the final boss of Lab 4?
Let's get into it. Level 4 PWM signals.
Similar to the square wave task, you have to direct your program to a highly specific pin. This time, you're targeting output port P2.5. Again, the discipline here is isolating your control to that single output line without disrupting anything else the microcontroller might be doing in the background.
And here is your highest hurdle, writing a program to generate exactly a 70% PWM signal. Unlike your previous square wave, which was a clean 50-50 split, this signal is asymmetrical. A 70% duty cycle means the signal has to stay at logic high for 70% of the time and logic low for the remaining 30%. This is incredibly practical stuff. In the real world, this exact timing technique is how we control the speed of DC motors, set the position of servo motors, or smoothly dim an LED array. Getting this right in your software is quite literally what makes complex hardware function smoothly.
All right, you made it. Let's wrap up this lab. To secure a win for Lab 4, just make sure your final submission clearly shows off these 4 compounding skills. First,
Prove you simulated that example code in Keil, routing P0 to P1. Second, document the code where you executed that bitwise XR inversion. Third, grab a screenshot, probably from your simulated logic analyzer, showing your perfectly timed 1 kHz square wave on pin P2.2. And lastly, show off that steady 70% duty cycle PWM signal running on P2.5.
As you power down your Keil simulator today, I really want you to ask yourself, how do these exact I/O manipulations unlock your ability as an engineer to bridge raw, invisible code with the complex physical world? Literally every robot, every smart appliance, every automotive computer relies on the exact principles you just programmed today. You aren't just writing loops and hex codes, you're learning how to make the digital world reach out and control the physical one. Keep that in mind and keep building.